Hello again. This is day 2 of chapter 4. This is Thursday. This is day 2 of Islamic Mathematics. I am not sure how this is going to turn out, which is kind of an interesting thing. I may end up stopping, not stopping partway through. I may end up finishing what I have prepared and then stopping and recording a second video of a little bit more. I'm kind of behind schedule right now, but I think I'm okay with that. I am talking about Umar al-Khayyami, or sometimes called Omar Khayyam. I am going to talk about al-Khayyami at length. I might finish everything I want to say about him and have extra time, in which case I will need to sit down and prepare a supplement to today's video for some more things at the end of chapter 4. If I use all the time talking about al-Khayyami today, I won't feel terribly bad about that. You read some interesting things about the second half. There is without a doubt good, sophisticated, fascinating mathematics after the time of al-Khayyami. But the al-Khayyami story, I think, highlights a lot of things about Islamic mathematics, and he's also one of my favorite mathematicians, so I'm biased, and I'm going to spend some more time on it. So there it is. All right, so let's get started. I want to give you a little bit of motivation for this. So let's, as is usually the case, come back to our course materials. Let me show you a picture. There's a picture. This is the Great Mosque in Isfahan, which is, I can make that larger. That's a little too large. Where Khayyami was working. Just looking at this, you see some important principles of Islamic art. Islamic art is extremely highly geometric. This is because part of Islam prohibits depicting sentient beings, something like it feels as if you're stealing their soul if you draw a picture of them or something. So because of that, you can't draw pictures of people hanging out in a field or something. So Islamic art, as I mentioned a moment ago, is highly geometric. It involves lots and lots and lots of symmetry patterns. Here is a close-up of one of those symmetry patterns from the Great Mosque. And you can see all of the detailed geometric work that's happening here. Let's see if there we go. So very sophisticated geometric patterns happening here, which is sophisticated geometry. This artwork inspires serious geometric questions. And we will talk about how artwork like this shows inspired Khayyami to compute solutions to cubic equations. Here's one more collection of pictures of some of the amazing details that you see in these places. So lots of great mathematics hiding inside of this artwork. I think I will continue to show you things before we start getting started. This is a article I came across earlier today about this very subject. Some of the pictures are about how these things called almonds, which we will talk about extensively for a while, can be used to create geometric patterns. So here is one of these almonds. You remember these almonds are two bright triangles that are congruent put together along their hypotenuse. So there's an almond, and it's used to create this pattern. And there's lots of other pretty pictures here. By the way, there's a picture again of the Chinese proof of the Pythagorean theorem, or the multicultural triangle theorem. And here's some more tilings you can make from these patterns, and some more and some more and some more things, and some more and some more and some more things. Lots of pretty pictures. And here's what is motivating al-Khayyami to answer a artist's question. So there's lots of different patterns you can make, but artistically, these middle kind are much more interesting. So there's a question that was asked to Khayyami, being a mathematician, saying, okay, if we, the artists, I'm not an artist, but in case, if the artists come to Khayyami and say, we want to make these patterns because they're prettier, this looks a little weird, this looks a little weird, this looks just right. So tell us how to make these patterns. What ratios do we need to use in order to make these patterns? What angles do we need? And so that's what Khayyami was motivated to look at. And we'll talk now about how to answer the artisan's question, as is indicated in this paper, an artisan's question. And we'll see what can be done with this. And by the way, here's other pretty pictures you can make once you get this idea. All right, and here's the answer, and you can read that there. I will talk through it up here. All right, so that's our setup. That's our goal. So what have we got? We've got these almonds. Yeah, that's somewhat unbelievable. It's going to end up being very tiny, and I'm already feeling bad about that, but oh well. And we have these right triangles. And one thing that I think you even saw in those pictures, we have this nice thing about these almonds is that we can find copies of them inside of themselves. So if we take a segment here that's the same length as that segment, then draw this in. And once we've done that, then not only are those segments the same length, but if we draw this in, then we can use something like hypotenuse leg congruent triangles. Since they share hypotenuse, they have a leg, and they're both right angles. Show that these sides are the same, and the same picture happens down here. And notice inside of the almond, I have these little almonds. And so this is geometrically pleasing, that we have these repeated patterns inside of themselves. In the particular case that the artisans came to Khayyami and said, can you make this happen? Was, can you make this side also be the same length as this side, which is that side, which is that side? Can you make all of those be the same? And what information would we need in order to do that? And so Khayyami says, okay, I'm going to work on this problem and see what I can do. I'm going to start putting some letters. I've been really trying to avoid lettering diagrams, but I think it's really is unavoidable this time. And so we'll call that H and this point up here F. And Khayyami says, well, what I want to tell him is this angle. And to find that angle, I would like to know some sort of coordinates for it. So to do that, I will put a perpendicular here and call this point D. And if we can find the ratio of AD to DB, I guess maybe the reciprocal of that, the ratio of dB to dA, that will tell us the tangent of this angle. And so then the artisans can go and make this angle, and they can make these almonds the way they want. And then that'll be great. And they can then use them in their artwork, and everyone will be happy, and we'll have pretty patterns on our buildings. So that's the idea. So we already know lots of things are congruent. We know, and we'll remember so that I don't forget, I did make AH congruent to AB. I made that way from the beginning. And from that, we saw using the congruent triangles, we get that BF is congruent to FH, is congruent to EG, is congruent to GH. Those are all those marked sides. And we want that FC will be congruent to AB. And we see how that goes. We can do some of this work. So let's see what Khayyami claims. So this isn't always going to happen. And he wants to make this angle so that that happens. And he claims, so eventually we'll need to worry about finding that angle, about computing it. That's a second question. He says, all right, well, what do I need to know about BD in order for this to happen? He says, for that to happen, if AH is to BD as AD is to DH, then FC will equal AB. And Suzuki's writing on this point was a little hard to follow, at least for me, and I'm always guessing if that's the case, maybe for you also. But that's what Suzuki says. Suzuki says that the artisans wanted this length to be the same as that length. And al-Khayyami says to them, okay, in order for that to happen, I need this ratio. And then al-Khayyami will do more math work, which we'll see as we go forward, to find out how to make this true. And so there's a lot of work here. So this is a long story, so brace yourself. All right. And sadly, I can't quite get there, but I can get close to there. I just don't have, I tried to dig up access to al-Khayyami's work. I'll probably end up finding it later this week or something, but this is what I have for now. All right, so what we're going to do is we are going to add one more thing to this picture, as if it's not cluttered enough already. We'll add this point J so that this is a right angle. Triangle. Maybe I should put something on the other side of the board. I'm not just working over here. That seems only fair. Triangle. Which one? ABD is similar, that's this triangle, is similar to triangle FJB. That's surely not true. That's definitely not labeled in the right order because the right angles don't even match up. BFJ, all right, good. So at least the right angles match up. And the other thing worth noting is that these angles are complementary. So, and so are these two. So this angle at A is congruent to the angle at B, and this angle at F is congruent to this angle at B. So these two triangles are similar. So we get some proportionalities out of that. So AB to BD is equal to BF to FJ. That shouldn't surprise you. AB, BD, BF, FJ. Okay, good. But we know some of these things. We know that BF is, among other things, well, actually, it's not the one I want to do quite yet. We know that a B, hold on. Hold on, I'm going to pause this, make sure I get it right. Okay, I got it. We have to use this. That makes good sense. So notice I have AB to BD. Notice also AB is the same as AH. So AH to BD is the same as AB to BD is the same as, apparently from our assumption, AD to AH. Good. And notice we also said that hold on a minute again. Okay, small mistake that's silly and no excuse for. This is, of course, DH. That's DH. Furthermore, what we have now is that notice DH and FJ are the same thing. These are actually equal just down here. So because of that, the top parts of these fractions have to be equal. So BF does equal AD. And in case we care, BF, which now equals AD, does also equal FH. And all these things down here, but that really, really doesn't concern us. All right, now from this fact, and this is where we will take some trusting of what al-Khayyami did, because I don't have access to this material yet and haven't figured it out yet. But from this, Khayyami gets to, as Suzuki indicates, AB plus BD equals AC. I don't currently see how that happens, but I believe it. He also gets to AB plus AD equals BC. I think, so the first one's going to be useful soon, I promise. The second one is useful right now, because notice if Khayyami can prove that AB plus AD is BC, well, notice that AD, we just said back here, is the same as BF. So this proves that AB plus BF is the same as BC. And notice that's AB plus BF is the same as BC. So that says, and also notice that FB plus FC is the same as BC. So this would tell us that FC were the same length as AB. So I personally do not see why we get from here to here, but I completely see if we get from here, from these facts to these sums, then we get what we want. And we also get something rather fascinating that happens here. So, all right, what do I want to keep of this mess? I think I want to keep these sums. AB plus BD equals AC, and AB plus AD equals BC. Admittedly, I don't want to keep the second one very much because I've already used it for its main purpose, was for getting that. All right. So that's part of the process. Khayyami says, okay, so in order to make these almonds the way the artisans want, he wants this proportionality to be true. But he's surely not going to be able to tell that to the artisans. They're not going to be able to make it so that those proportions are equal. They want something that they can measure and make using measurements. So Khayyami doesn't yet have an answer that he can return to the artisans. So let's see what happens next. Notice that triangle ABC is similar to triangle ADB. This is the top of the almond. They're both right triangles. Oh, we haven't seen the other one. This is this triangle here. They're both right triangles, and they both share angle A. So these are surely similar triangles. So this tells us that AC to AB is AB to AD, just from standard proportionalities of similar triangles. And now let's look ahead to see where Khayyami is going with this. What he wants to do is find this angle. So he wants to find the ratio of BD to DA. Just to keep the numbers somewhat nice, he says, well, I can make this any size I want. He's just looking for a ratio, so you can pick one of the numbers. So Khayyami says, let's call BD 10. Okay, I mean, you can do that. 10 what? 10, that's not the one he wants to call 10, though. Sorry. Let's call AD 10. You can do that also. 10, whatever, 10 times the length of that thing. And he'll call BDX because he's trying to find out what this ratio is. So his goal is to figure out what that length is, so he can either use trig tables that Abu Wafa developed, or he can just tell them make these two lengths, and you make the angle that you get by making those two lengths. So that seems like useful information to have. So what Khayyami is trying to do now is to say, if this length is 10, what is that length? And so he goes through some work to do that, and this is what we're doing now. So, okay, so we have this proportionality, which we could cross multiply. It says AB squared is 10, because, oh yeah, AD is 10 times AC. And, oh, remember, AC is AB plus BD. Oh yeah, and BD is X. So now we have an X inserted into this mix. Okay, fine. So that's one thing. But also that's probably the harder work. If I had told you, hey, BD is X and AD is 10, you would have told me something about AB squared. I know you would have. You would have told me that AB squared is also equal to X squared plus 100. It's that multicultural right triangle business again. So, okay, that tells us we can make a couple substitutions here. Yeah, I think I'll keep this down here for now. I will come up there eventually. So that tells us X squared plus 100, which is AB squared, yeah, equals 10 times AB. Oh yeah, that's apparently the square root of X squared plus 100 plus X. All right, notice al-Khayyami is well on his way now. He has an equation that involves numbers and X. And he seems like, yeah, I could be able to figure this X out and then tell it to the artisans, and they can make these almonds and everyone will be happy. And so he goes forward, and maybe he multiplies the 10 out, or maybe even better divides both sides by 10. So we get, maybe I'll put this here. X squared over 10 plus 10 is the square root. It's nice to not have that 10 cluttering the square root in. Move that X over so we clean out the square root from it. And now square both sides so that we can get rid of the square root. Intriguingly, when we do this, we get a 4th degree polynomial, which is kind of disturbing and also interesting because, as we will find soon, to Khayyami, squares are squares, cubes are cubes, they're physical objects. And I'm not sure what he makes out of fourth degrees, but thankfully he doesn't have to bother with it too long because these hundreds cancel. And when those hundreds cancel, we can move the x squared over to this side to make 2x squared, move the negatives over to the positive side just to give things physical meaning. So we have x over 400 plus, no, x over 100 plus 2x squared equals x cubed over 5 plus 20x. That looks good. And now multiply the whole thing by 100 because we don't like fractions. And also, oh yeah, divide the whole thing by x because we really don't like it being fourth degree. So x cubed plus 200x squared equals 20x squared, that's right, plus 2000, not x anymore because we did divide the whole thing by x. And we get this. And so Khayyami looks at this situation and says, all right, I'm back thinking about these artisans and these almonds. I want to tell them how to make this thing. I need to tell them the ratio of these two numbers. I really want to know what x is. And apparently, to find out what x is, he needs to solve a cubic equation. All right, that's an interesting reason to need to solve a cubic equation. It's a strangely practical reason to need to solve a cubic equation. So the next thing Khayyami does is learns to solve cubic equations, and he writes about it. So I'm going to take most of this away, open up Khayyami's discussion about cubic equations. That's not it. That's his discussion about almonds. Here's Khayyami on cubic equations. And I think I'm not going to spend time erasing because I think I'm going to spend some time erasing. I will let you look at that a little bit. I will also say I don't have easy access to how Khayyami solved cubic equations like the one we just made up. I will remind you of what we saw with al-Khayyami and Ibn Turk last time. Remember, equations are geometric things. They're talking about, I am not sharing my screen. That's interesting. You can't see that. You've just been watching the erase, which I guess is fine because there wasn't terribly much to see, but there we go. So I'll remind you that these are geometric statements. When we did this with al-Khayyami and Ibn Turk, squares were squares. X was a side of a square or a root of a square, and numbers were numbers, but they really meant area. And because of this, you have all these different kinds of quadratics, and you remember al-Khayyami broke them down into different cases. You have all these different kinds of cubics. This is a cubic that's not the kind that we were just talking about. It's a different kind. This is, as you see here, now you can see it, this is a solid cube plus squares plus edges equal to a number. That would be, yeah, I'll try to switch back and forth and see how that works. That would be a solid cube plus edges plus squares plus edges. And notice we're going to use b squared times edges because we want everything to be three-dimensional. So this is some square length times an edge. This is some length times the square so that everything here is three-dimensional. and it equals some number, but that number, remember here, is really a volume, because this is something that did have geometric meaning for al-Khayyami. All right, let's go back and see what he has to say about that. Yes. Oh, that worked, great. All right. So he says, we draw BH to represent the side of a square equal to the given sum of the edges. That says in our terminology, BH in his picture is B. It's the side of a square equal to the sum of the edges. The sum is the total, the number of the edges. And we do have that square incorporated there. And then we think about, although he doesn't draw in 3 dimensions, we think about constructing a solid whose base is the square of BH, which equals the given number. The given number by which he means the volume that's out here that we have called C. Let the height BG be perpendicular to BH. So you can see, in case you care, here's BH and here's BG, and it's perpendicular. That doesn't concern us terribly much yet, but it tells us how to do some things. So in particular, what did he say? He said BH squared times BG equals C. BH squared is the base, BG is the height, and altogether that gives our area BG. I'll let you see this for a moment. Here it is. Ta-da. Now I will take it away again and let you see what Khayyami has to say. There we go. All right. Somehow we need to put A in this. So he does that next. We draw BD. Here's BD. Equal to the given sum of the squares along BG produced in the same line. So we have BD is equal to A. And you don't need to see that because it just said BD is equal to A, which he pretty much says there. He's not using the A, B, and C like we would. They're not using any of these variables like we would. This is what they've got. I'm trying to make it clear to you. All right. Draw on DG as diameter a semicircle DZG. All right, well, I believe you. That looks like a semicircle. So great. We have no idea, by the way, why he's doing this, but it's going to work out magically, wonderfully nice in the end. And complete the area BK. That is, make this into a rectangle. He's labeling rectangles by their corners. Okay. And draw through the point G a hyperbola with the lines BH and HK as asymptotes. All right, that's interesting. So you see it there. This is the little bit of the hyperbola. And so we're going to draw a hyperbola with that condition. Now, your favorite hyperbola, happily for these purposes, is 1 over x equals y. A more generic hyperbola is maybe some constant over x equals y. In particular, what that tells us, maybe I should show you this for a moment. So your favorite hyperbola is 1 over x equals y. A more generic one is some constant over x equals y. In particular, that tells us that x times y is a constant. And x and y, because we were told, oh yeah, so x and y, here's x and y, are, what are they? They're the distances from the asymptotes. Al-Khayyami knew this a whole lot better than you do. Al-Khayyami knew that a hyperbola is defined to be the set of points where the product of the distance to the two asymptotes is constant. And this is the property that he will use over and over and over again. Well, not that much, but he'll use it to good effect here. So he's going to use that. He's not calling things coordinates though, but the distance to one asymptote times the distance to the other asymptote will be the same no matter where in the hyperbola we look. So let's go back and look at the picture. Let's go back and look at the picture. Come on. There we go. So in particular, since this is a hyperbola, we have things like h times b for point G, by the way. Here's the distance from this asymptote, equal hb times hk. That's the product for G. So hb times hk equals the same product for this point Z up here. So that should equal ht times ha. Those are the distances from the two asymptotes. All right, so that's what we know from the fact that this is a hyperbola. What Khayyami says is, and can we find this? Oh, you should ask, wait, how is he drawing a hyperbola? He's drawing a hyperbola by plotting a lot of points. By very carefully starting with the point G, because that's the point he wants the hyperbola to go through, and making other points that have the same product of distances from the asymptote. So we could measure one distance and find the other one and keep going and plotting points that way. That is what he's doing. So let's see if we can catch up here. Let it intersect it. Let the hyperbola intersect the circle at point Z, whose position would then be known. So point Z is defined to be the point where the hyperbola intersects the circle. And then from that, we can find BL, because BL is the same as ZA, but it's more central to the action. We find BL, and I'll tell you the punchline, because we have some work to get there. BL is going to be our X. And notice this is the way al-Khayyami solves a cubic equation. He solves a cubic equation by drawing some lengths of the different coefficients on a picture and says, if I can draw these lengths, then this piece here will have the length I want. And so I can measure it as exactly as possible. This is not an approximation. This is an exact solution to a cubic equation because you can draw your pictures as exactly as possible and measure them as exactly as possible. He says that those two areas are the same. Remember that from a hyperbola. He will use slightly different dimensions for them, and I will skip a little ahead of his text. He will use ZL. All right. So he says that this rectangle then has the same area as this rectangle, because when we multiply the coordinates, we get the same numbers. And then he says, wait, but they share this thing in common, so forget that. That doesn't help us much. So then he says this rectangle up here has the same area as this rectangle over here. All right, so to compute the area of the top rectangle, he has ZL times BL. To compute the area of this rectangle over here, he has TL times LG. All right, I will let you stop looking at that picture for a tiny bit while we do some algebra along the way with our geometry. So we can translate this into some proportionalities. ZL to LG is TL to BL. Okay, great. But if you look back at the picture, and I will let you do that just because it seems only fair. TL is the same as BH. And the ones with B's are more important in direction. So this is HB to BL. All right. And where are we following what Khayyami says? By the way, this seems worth noticing a little. All right, so the area of the two rectangles are the same. This is from the property of a hyperbola. Now make HL common. They have that rectangle in common. There remains, after we subtract it, the area of this rectangle equal to this rectangle. Therefore, we have a proportion, and that's the proportion that we had to begin with. And because HB equals to TL, we get a new proportion. And then he says, and their squares are also proportional, but their proportions are equal to something. All right, so let's stop that for a moment. He says, so their squares are also proportional, which is, you start to wonder why he would care about that, but surely true. And then he says, but ZL to LG, this proportion here, is equal to DL to LG, he says, because of the circle. And I look at that and I said, what? What do you mean because of the circle? So let's look back at the picture and see if we can see why because of the circle. Back at the picture. Oh, by the way, he does say this. Where does he say it? Here it is. But the proportion of the square of ZL to the square of LG is equal to the proportion of DL to LG because of the circle. What do you mean because of the circle? This is what he means because of the circle. Notice we concern ZL, LG, and DL. Those are the quantities here. Notice in particular that if we drew this and connected ZG and ZD, we'd have some triangles inside of a semicircle. And there's nice things about proportionalities of triangles inside of semicircles. You can see that some of these triangles would be similar. You could see out of that ZL, let's say to LG would equal DL to ZL. And from that, well, we can get that ZL squared is DL over LG. No, it is not. We get that ZL squared is DL times LG. And then if we divide both sides by another LG, we will get what we wanted. So this follows by those triangles that al-Khayyami is so familiar with, he didn't even need to draw them. He just says, this is the way circles work, you know that. And then from there, he divides both sides. So cross multiply, get ZL squared equals DLLG. Divide by LG squared, and you will end up there because of the circle, or so he says. All right, what does he say next to us? We are actually getting kind of close to solving a cubic equation using a geometric diagram. You can see we're running out of text. This is near the end here. So where are we? We just did because of the circle. There, because of the circle. Therefore, the proportion of the square of HB to the square of BL is equal to DL to LG. So we had these squares were equal to that. So by transitivity of equality, which aptly al-Khayyami doesn't make a big deal about. We have HB squared to BL is DL to LG. That's good. And he says, so now he starts to think in terms of area, volume actually. Therefore, the proportion of this is to that. Therefore, the solid whose base is to the square of HB and whose height is LG, what he's doing is multiplying this across. So we have, and I think I'll come up here, HB squared times LG is equal to DL times BL squared. He's just multiplying this proportion out to give us something about volumes. Therefore, the solid whose base is the square of HB and whose height is LG would equal the solid whose base is the square of BL and whose height is DL. Okay, great. But this latter solid is equal to, so let's go look at our picture to see where DL is. Here, we're coming up and looking at the picture. DL is apparently BD plus BL. I'm going to let you stop seeing the picture for a moment. If I come up here, I have HB squared times LG equals DL is BL plus BD times BL squared. Okay, all right. We are getting somewhere. Remember, BL squared, Khayyami thinks is our x. He thinks it's going to satisfy this whole equation, so that's his goal. And he now multiplies this out and says this is BL cubed plus BL squared times BD. He's making progress. If you see, if he's claiming that that's x, he now has x cubed plus BL squared is x squared. BD, oh, by the way, that's a, and it's multiplied by a squared. So that's good news. That's good news. Let's see what he does to finish things off here, because he is almost done. All right. Therefore, the solid and which is equal. There we go. But this latter solid is equal to the cube of BL plus the solid whose base is the square of BL and whose height is BD, which is equal to the given sum of the squares. All right. So BD, and he's reminding us that BD was the sum of the squares. That is how many squares there are, which was A. All right. Now we make common. And I think our translator is kind of double translating so he's translating from Arabic, and then we add is translating from the translation to something that's familiar to us. We add the solid whose base is the square of HB and whose height is BL to both sides. So we have over here HB squared times LG, and we are adding the solid whose base is HB squared. Okay, good, that's comforting, it's the same kind of thing, times BL. And on the right-hand side, we have x cubed plus x squared A plus HB squared BL. So he's adding that to both sides. Let's stop this so you can see what's going on up here. All right, so I had these two things equal before. This one was just the same thing by translating into what we declared as variables so that we could recognize what we were talking about. Then he has this, and some things are great already. HB squared, HB is the same as BH, is B squared times BL, which is our x. So this is B squared x. So we currently have x cubed plus x squared A plus B squared x on that side. Only thing we need is if the other side is really going to be C. when we see that it's HB squared times LG plus BL, and if we're, well, I'm not going to spoil that. We'll get there soon. Let's look back at the picture one last time. This is our last time to look at the picture. And we have HB squared times LG plus BL. And yeah, LG plus BL surely equals BG. So that gives us HB squared times BG. And I think we're done with that once and for all. HB squared times BG. Hey, let's see. So the measurement that he made of X does satisfy X cubed plus X squared A plus B squared X equals C. He did find a length that he could go and measure, that he could construct given the inputs, so he could make the lengths A, B, and C whatever he wants, then construct this diagram the way he said to do it. Then he proves if you do all of that, you can measure X, and by that you can solve this cubic equation. It is worth pointing out this cubic equation is not exactly the same form as the kind that had to do with the almonds, but this is how people, al-Khayyami in particular, were solving cubic equations geometrically. It's a very fascinating way to be working. It's very different from the way you would work. You could, however, trace through all of this and find what you would like, an equation for X in terms of A, B, and C. All of this are things you can compute. You know about circles, you know about hyperbolas, you know about proportions. Going through all those computations, you could dig through the algebra and find all the different lengths in the whole picture. And as a consequence, find X in terms of lengths A, B, and C. But for them, it was constructing a line. I'm going to stop this now, not knowing how long it is, hoping I still have some little extra time to talk about a little more. If I don't, that's the end of the lecture today. If I do, there will be a supplemental video. Thank you so much for our time with al-Khayyami.